Series of lecture we were discussing the properties of Schrodinger equation, that is, we have interpreted the wave function or have stated the boundary condition to be satisfied by the wave function, and we have applied the boundary condition to few simple cases. Furthermore, we have talked about the general superposition principle and found out how the completeness of the set of eigen functions of the Hermitian operator can be utilized to express any general state. Today we shall talk about the measurement. As we have stated earlier, that in quantum mechanics, performing a measurement and non-performing a measurement is big different. There is a big difference. So the theory must include within it the aspect of measurement. As per correspondence principle, any dynamical variable of classical mechanics, dynamical variable A of classical mechanics is replaced by the corresponding Hermitian operator in quantum mechanics. This is in classical mechanics. This is quantum mechanics. It is a variable and this is an operator and Hermitian operator. The operator has to be Hermitian. So we know that this operator has certain eigenvalue equation. So A operator, when operating on X, gives you lambda times psi, and if we consider the spectrum, then it is this. This equation may be interpreted as follows. Let us consider this is to be the operator corresponding to the measurement of position. So it is the position measurement operator. So while we are performing some measurement on quantum mechanical system to measure the position of a particle, we have to put some effort to measure the mathematical representation of this act of measurement is included in it, and whenever we perform measurement we get certain value for the position. That certain value is the eigenvalue of the operator. So this aspect says that whenever we perform any measurement of a dynamical variable, what we get is one of the eigenvalues of the dynamic corresponding operator. But in quantum mechanical system, if one performs the same position measurement repeatedly, he gets different values for the position, because it is a microscopic system and we do not know beforehand what is going to be its specific value. That is to say, whenever we perform the measurement on a large number of identically prepared independent system, that is the ensemble in the slang, that is to say ensemble in the language of statistical mechanics, we get what is the average of over these microscopic values. This is called the expectation value. Expectation value. This is the average value, or ensemble average value. Whenever there is a distribution of certain quantities, or say there is a distribution function of x, then we say that the distribution function is to be normalized. So f of x dx is normalized, and then if you want any quantity u, then the average value of u is given by this f of x u dx is the average value, provided the x quantity the function distribution function is normalized. If it is not normalized, then it has to be divided by f of x dx. In quantum mechanics, we are our distribution function is the rho of xt, and which is equal to psi star psi. So the expectation value that we have talked about must be given in terms of this. The expectation value is denoted by the operator A, and this is the expectation value. And if we write it in terms of wave function, then it will be A operator, and these two will come. The operator A is an Hermitian operator. So we write it in this fashion: psi star xt A operator psi of xt dx as the expectation value. Note that it is a Hermitian operator, so n by n matrix. This is a column vector n cross 1, and this is a row vector 1 cross n. That's why we have done what in place of f we have written psi star psi, and this A vector has been sandwiched between psi star and psi so as to maintain this matrix relation. This is called the expectation value of an operator. So by this postulates of quantum mechanics, one relates the experimentally observed value with the property of the operator. Now we come to the uncertainty principle. Earlier we have stated that if we have to canonically conjugate variable, then simultaneous and precise measurement is not possible. Let me see this aspect in terms of superposition of states. First, let me define what is uncertainty. If we think it in terms of error, the error in a quantity is most suitably represented by its standard deviation, because standard deviation is suitable for further mathematical calculation. An uncertainty in the measurement of a variable is the lack of information regarding its value. So we can give a standard deviation type definition for the uncertainty. Let us consider a quantity x, discrete variable x, which is xi, with I is equal to 1 to n. Then the average of x is given by 1 over n summation over xi. If we have a continuous distribution, then continuous distribution function is given by distribution function is given by this, and the average value is given by average value is given by integration f of x dx as the average value. Here we have assumed that it is normalized, f is normalized, and the standard deviation in x square is given by 1 by n summation over I xi minus x average whole square. This is 1 upon n summation over I. This is xi square minus 2x bar xi plus x bar square. This goes to 1 by n summation over xi square minus x square average. So this is x square average minus x average square is the standard deviation square. In this case, the sigma square is given by similar expression f of x square dx minus integration f of x dx square. So if we take this definition as the uncertainty, then we define uncertainty uncertainty in the measurement of A is delta A square. This part is the expectation value of the operator square. So this is A operator square expectation value, this is this part, minus A operator expectation value square, this is this part. This is the definition of uncertainty. So this is the uncertainty in A. In the measurement of A. Now consider that the system that we are considering is in one of the eigenstate of A. So we first define delta A, uncertainty in the measurement of A is equal to a square expectation value Now we consider this case that the system is one of the eigenstate of A. So A operator's eigenstates are now the state measurement where I is 1, 2 and the system is already in one of the eigenstate. So if we apply A on psi, A operator on psi, it is A operating on psi I, this is lambda I. This may create confusion, let K, any of the eigenstate. K is one of these I, say K is equal to 5. And A square phi is A times lambda k will not be operated on this, so this is lambda k, A operator on phi k is equal to lambda k square phi k. So the expectation value of A for phi star we write lambda k star. A lambda, for A lambda we write this. Since this is normal, this is simply lambda k. And sorry, first is this, then since the state we have assumed to be this, it is phi k star and the quantity is lambda k square now uncertainty in the measurement of A square is equal to for this it is lambda k square and this is lambda k square which is 0. So there is no uncertainty that when the measurement is performed on a system which is already in one of the eigenstate of the dynamical variable, there is no uncertainty. The quantity can be measured as precisely as we wish. Now we consider the system is in a superposition of state. So the system is no longer in one of its eigenstate, but it is in a superposition of state. So we write it Ci phi I per sum over I. And this is the eigenvalue equation. So A operator operating on psi gives you summation Ci lambda I, sorry, k, yes, this is, and expectation value of A operator is psi star A psi dx. Now for the psi star, we shall write the I sum j sum. J sum stands for Cj star, and this when operates lambda I Ci lambda I, and within the, this is delta Ij. So the result is summation over I lambda I Ci square. Similar result we obtained with the energy operator. Here we found that the relation is not only valid for energy operator, but rather for any dynamical variable represented by the Hermitian operator. And coming to the A square average. If we operate A once again the net, what we'll get? I will get summation over I Ci lambda I A operating on phi I. So this is summation over I Ci lambda I square. So this result is again summation over Ij Cj star. For this we get Ci lambda I square, and this is Cj star Ci dx. This is delta function. So the result is Ci modulus square lambda I square. So this results to be this result is C1 modulus square lambda 1 plus C modulus square lambda 2, and only the 1 term appears. And if you square it, this result is lambda 1 C1 square lambda 1, sorry, C2 square lambda 2. If you square it, the first term will be C1 to the power 4 lambda square. So the cancellation is not done, and we conclude that delta A square is not equal to 0. So the conclusion is that whenever we are performing measurement of a dynamical variable, if the system is already in one of its eigenstate of one of the eigenstate of the variable, then there is no uncertainty, and the measurement can be performed with utmost precision. But when the system is not in one of its eigenstate, rather it is in a superposition of state, then there will be some non-zero uncertainty in the measurement of the variable. Now we come to the simultaneous measurement of two variables. Let us consider variable A and variable B, when they are dynamical variable, and in quantum mechanics they are represented by the operator A hat and B hat. So we have two operators A and B. Dynamical variables were A, say position, and B momentum. So in quantum mechanics they are operator, and the eigenvalue equations are written as like this: A operator operating on phi ai gives you lambda ai phi ai, and similarly for B operator we have phi I b is equal to lambda I b phi I b. Now let us consider that system is in a state governed by this. If we perform measurement, then perform measurement on the A, then the system is brought into one of its eigenstate of the operator. So the state is, say, phi I a is obtained. This phi I a is not an eigenstate of the operator, in general is not an eigenstate of the operator B. So it can be represented in terms of the eigenstates of the operator B. So we write it as sum over J C B I, sorry, C B J phi J B. Now what happens? For the system was originally in a superposition of state, which includes all the possibilities of the this phi is a superposition of all the possible states on the measurement of the variables A and B. When a measurement A is done, then from the superposition of state the system comes to one of the eigenstate of the operator A. Say this eigenstate is this. So if this is in general not an eigenstate of B, so the eigenstates of B again forms a complete set. So we write it in terms of the linear combination of this. And whenever one performs a measurement on this of the operator B, the system is dragged down to one of the eigenstate L of B. Now we use the operator in a reverse order. First we use the operation of B. Then when the system comes to one of the eigenstate of operator B, which is written as summation over J C A J phi J A. Now if we perform the operation measurement of A, then it is psi k of A. So we see that on reversing the order of measurement, we in general land up at two different places. There is an exception. The exception is that when two operators A and B commutes, then we know that two commuting operator has the same state, same eigenstates, same simultaneous eigenstates. That is, this state would also be an eigenstate of the operator B and the vice versa. Then once we perform the measurement of the variable A on the superposition of states, system is taken into one of the eigenstate of the system of the operator A, which is also an eigenstate of the operator B. So here we can measure B accurately, because the system B is the system was already in one of the eigenstate of B. In other words, measuring B first, the system is dragged into one of the eigenstate of B, which is also an eigenstate of A, and we can measure A precisely because already the system is in one of the eigenstate of A. That is to say, whether the simultaneous and precise measurement of two operators is possible or not depends on the commutator relation of the operator A and B. The basic commutator relation that quantum mechanics assumes is the x operator px operator is equal to IH cross, and such things x operator py operator is equal to 0. So these are the types of commutator operator that quantum mechanics assumes, and if one assumes this is the basic commutator relation, it immediately leads to the definition of or the expression for the momentum operator in position space to be minus IH cross delta x. We shall need few basic commutator relation in for subsequent calculation, but we shall devote an entire lecture on the commutator relation. So I am skipping any further discussion on the commutator relation for the time being. Just as a passing comment, the Schrodinger formalism that we are we have adopted here solves the problem by solving differential equation. There is an alternative approach of quantum mechanics which is called the matrix mechanics, developed by Heisenbach, Jordan and others, which is an abstract mathematics which relies on such commutator relation and develops the thing using the commutator relation. Now we come to the time evolution of a dynamical variable. Consider a time evolution of the expectation value of a dynamical variable, which is very important. Time evolution of the expectation value of operator A. So we have an operator. Our basic question is how does this expectation value changes with time. That is, we want to know what is the value of this thing. This is the expectation value. What is the time rate of change of this? We write it as ddt, and for this we write psi star a psi dx. We are still in one-dimensional problem, and for the sake of brevity we have dropped the argument x and t. These are actually function of x and t. Oh, okay, let me write it in detail. So we take this integration within this, and this will be partial time derivatives, because when we integrate this out over x variable, the quantity does not depend on x anymore. It will have entirely time dependence. So we have written a ddt. When we take this operator, the time derivative within the integral sign, then this integration is not carried out, and the integrand is a function of x and t, both are x and t. So we use partial derivatives. So this is psi star a del psi del t. It operates on this, plus it operates on this, finally if the operator doesn't have any explicit time dependence, then it is 0. Now let me see what it is. we know the time dependent Schrodinger equation is IH cross del psi del t is equal to H psi, for psi of xt. So del psi del t is equal to 1 upon IH cross H psi, and del psi star del t is equal to minus 1 upon IH cross this will be H psi dagger, and this will be minus 1 upon IH cross psi star H. Since H is Hermitian, H dagger is H. So you use this. So for this thing, mine IH cross 1 upon IH cross. This integration psi star A for this it is H psi for this term this is minus, so we have minus psi star H. This is from this part and this is A psi. Let me denote once again. This term contributes this part, and here this contributes this part. This is very important. Dx, and this term is left. This term can be written as expectation value of dA dt. We have used just. Now you see that this is 1 upon IH cross psi star AH psi dx plus del A del T. This is known as Heisenbach equation of motion. Equation of motion. This equation of motion in terms of this commutator bracket, and in classical mechanics a similar equation is obtained in terms of Poisson bracket. Now the commutator relation AH is defined as AH minus HA. In algebra involving variables, we know that the product is commutative. So AB and BA are the same. AB is equal to BA. But in matrix algebra or in operator, the operator may not commute always. So we get this thing. To proceed further, we will need some relation of this sort. A operator, and there is a combination of BC operator. In writing, if we use this definition, this is A followed by BC, and reversely this is BC followed by A, and the hats are over all this. We write it as A, B, C. We subtract a term B, A, C, so that we have to add this term, and the original term is BCA. If we take C common from these two terms from the right we get AB minus BA times C, and if we take B common from the left from the last two terms we get AC minus CA. This is AB commutator, so the relation is A commutator B, C appearing from the right, plus A commutator C, B coming from the left. The rule is A will commute with B and C in turn. When A commutes with B, C will come to the from the right as it is on the right, and when A commutes with C, B will come on the left as it is in the left. So we shall use this relation to find the expectation value of X and P operators. So if we consider a one-dimensional particle subjected to a potential V. So H Hamiltonian is P square by 2m plus V operator. It is a function of X only. So now if we are to find out ddt of X, we are to find out minus IH cross psi star XH psi dx plus 0, as the position doesn't have any explicit time dependence. Now let me evaluate the term X operator, X commutator H. Now XH commutator is X operator, and for H operator we write P square operator by twice m plus V operator of X. So first this will commute with this, and since 2m is a constant is taken out, so X P square, and this is X commutes with V of X. This V of X can be written in power series of X, and which commutes x to the power m, x to the power n commutes with each other, so this term is 0. So we are left with this term. So this is 1 upon 2m. X commutes with P, X commutes with P, P coming from right, and we have written this P square as P into P, P times P. So 1P comes, and this is IH cross, this is also IH cross. So twice IH cross, this is twice IH cross P operator by 2m. This is IH cross P operator by m. If we write this, we get IH cross, this IH cross is there, and there will be IH cross in the numerator, which comes from this commutator bracket, and we have psi star. For this we have P operator by m, so m is also taken out, P operator psi of X. By definition, this is the expectation value of P operator, so it is, we know in classical mechanics that P is equal to mv, that is the classical relation. This is the, as if the class velocity, this is the velocity and this is momentum, and velocity and momentum is related by this. In classical physics, velocity is P by m, here this relation holds, but not in terms of the dynamical variables or the operators, but in terms of their expectation values. This is one of the important theorem of quantum mechanics called Ehrenfest theorem. Ehrenfest theorem. The theorem is not yet complete. It has another part, that is the we have to calculate the expectation value of P operator. So if we want to find out the expectation value of P operator, we have to perform the commutator of P with H. Let me first do that. P operator operating on this. This is P operator and this term is 0. So this is P operator operating on square and this is P operating on this. The conclusion will be different. Here this is 0 and we are left with this. So we have to find out P, the commutator of P and potential. So the task reduces to the evaluation of commutator of P operator with V. This basically reduces to we consider this thing. P psi of x. So this is PV operating on psi of x minus VP operating on psi of x. For P I write minus IH cross del del x minus IH cross del del x, which operates on V times psi, and here it is minus minus, so minus IH cross is taken common, minus IH cross is taken common, so this is del del x operating on this, and here we have minus V del x operating on psi. In quantum mechanics, we should be careful about using the third bracket as it denotes the commutator. So this has two terms. So this is minus IH cross. It has two terms. One is del V del x psi and another one is plus P del psi del x, and this is minus V del psi del x. These two terms cancels and we have minus IH cross del V del x operating on psi. So we can conclude that PV commutator is minus IH cross del V del x, and this is equal to plus IH cross 4F, x component of the force. So if we apply this Ehrenfest theorem to operator P, we get ddt of Px operator, specifically Px operator, this is psi star Pxh psi dx plus 0, because the operator doesn't have any explicit time dependence. For this part we write IH cross term is missing, 1 upon IH cross. So we have IH cross and this is IH cross. This IH cross is from there and this IH cross is from there. Psi star fx psi dx. This is the expectation value of force. So this is, again we find that the force is time rate of change of momentum, but this relation holds in quantum mechanics in terms of expectation value. This is one important thing, relation in quantum mechanics, that is to say the classical result holds in terms of the expectation value.